Good evening. Uh, Today we will start with the week 6 NPTEL course on user centric computing for human computer interaction. And we will do some problem solving like we have done in the previous weeks. So we usually what we have how we have constructed these sessions is we first go through some part of the content of that week, and then we solve problems, assignment problems that were asked in the last year of that same week content. So I've grouped the questions in such a way that they will follow the order: explanation, question, explanation, question. So that is how we will go about doing the revision. Okay, we will. You can post your questions on the chat window. When the respective problem comes up, we will address those problems, those questions. Important announcement about this week's content is focused on the assignment questions. So there are questions which will be covered within the last year's assignment, and what is asked I have focused on that. So the material that we will study before solving the questions is also aligned to those questions. Okay, so that you can answer probably this week's as well as last week's this year's as well as last year's question assignments. uh, Now, let me introduce myself. I'm Spruha Satavadekar. I am from IIT Bombay. I am doing PhD in educational technology over here. And I have done this course on human computer interaction during my work as a educational technology student. So now that we are also working on user centric computing, it is kind of a part aligned with human computer interaction, where for the course human computer interaction, the focus was mainly on design part of it, how to make the design user centric. And now that we are studying computational models, in the last week we did some computational models. We previously have gone through some descriptive computational models. We will go through that revision today also. Now that we are studying all the computational aspect of it, this course is mainly more about the how to make computation more user centric. So not only the design but also computation. So welcome both of you. Thank you for joining today's session, and I am also going to request you all to provide feedback if you are attending the session, because that feedback has gives me a lot of ideas about what to do next and how we are going about. Okay, if you are also attending these sessions, we are posting the recording of these sessions on YouTube, and in YouTube you can post comments so that we can modify the next session, incorporate your comments in the next session. Thank you. So now we will begin with the like week 6. Before we go into the week 6, we will give a recap of week 3 and week 4 and week 5 content, a little bit of recap which is needed for this week 6. Okay, so initially in the week 3 we learnt about some user centric softwares, the types of it. So the user centric software can be of two types. One is the interface layout changes. Depending upon the interface layout changes, whether it changes or not, depending on the users input, there are two types. One is adaptive and the other one is not adaptive. So the adaptive user centric software takes users input from the input provider, and it utilizes it to predict the next state of the layout. Basically how the interface looks, that is the interface layout. To make it user centric, there are two ways. One is continuously take in the user's input, capture it, and then make the layout adaptive. So that is the adaptive way of doing it. Whereas the other option is not to take the user's input, not to capture the user actions and performance in terms of actual user input, but to capture some information about the user behavior in general, not the specific user. Okay, and make it adaptive, make it a non-adaptive way. So the non-adaptive user-centric software, it's still user-centric because it considers some of the parameters which are taken out of theory or taken out of empirical examination previously done by the designers. So they don't, what they don't capture is the user specific new users input is not captured in it. So input provider is not required in the non-adaptive case. The input provider is not required, and then user state is calculated without the input provider block. Okay, so the interface design does not change as per the user input. So these are main two types. So there was one question in the old assignment: in software development, we use models to develop a theoretical view of the characteristics and behavior of a software. Is it true or false? Correct. So the answer is true. Semi Now the next part is a semi-automated and automated approach. Even though you are performing the adaptive or non-adaptive, irrespective of that, there is this semi-automated and automated approaches are there of making the computational models and creating this applied application layer. So what happens in semi-automated one is that the comparison of different model parameters and the decision is taken by designer. So the comparison is done, many models are created, and then the designer finally takes the choice whether to go for uh, model which gives us a lower time, or whether to go for a model that gives is lower in speed, so it takes more higher time, but it is more accurate. So that kind of decision is done by the designer, but same thing can be automated. So if you put the logic of the designer in terms of computation, then that decision making can be done with automation as well. So in that case it is a automated type. So if we look at the model based design, based on the design type, there are two types of model based design. One is adaptive and non-adaptive. Design type as in whether the interface layout changes based on specific users input or not. And then design scope. So design scope is whether the design takes care of making the decision, or whether the designer needs to be there to make the specific decision about the choice of model. So that is the types based on design scope, what all the designer can do. Okay, so you can have adaptive design models in semi-automated as well as automated design. Similarly, you can have non-adaptive design models which use automated as well as semi-automated design. Now this content, where is it coming from? It is coming from a merging of week 3 week 4 content, and we are merging it with the case study video that we cover in the this session. So a lot of disjointness was there when I went through the material, so I tried to combine it and present it. Next we will go to the question. We do not require dash to design non-adaptive layouts following a semi-automated approach. B, input provider. Very good. So I think that whether it is irrespective of whether it is semi-automated or automated, we can still have the answer will still remain as input provider because it is non-adaptive. Okay, so this question may be, tweaked and asked in the exam, whether we're removing the semi automated, replacing it by automated. The answer will still remain the same because input of the user is not considered in the non-adaptive layouts. So, and then we will do a little bit of recap of the user-centric models. So, there were two types. One was descriptive, and then the other one was predictive or performance or predictive engineering models. In the descriptive models, we studied three examples. One was the tree state model for graphical input device. There we looked at the examples such as stylus or touchpad. So how they capture the behavior of users while pointing, using the pointing devices. Then we studied the Giard's model of bimanual skills. It talked basically about entering the typing and sketching kind of thing, drawing behavior of the user, where hand movements, specifically hand movements, were considered. Then so basically it gave out the idea that the based on the prominent hand of the user, the other hand which is not prominently used, preference the non-preference hand, that takes care of creating the kind of boundary for the imaginary boundary for the user to act in to utilize their preferred hand and type out things or draw things or write things. In the third descriptive model, we went through Norman's model of interaction, where we looked at the gulf of execution, evaluation, how the it was a relatively detailed model about mental, sensory motor activities. So there were mental activities such as defining the goal, thinking about the objective, and then for creating the stepwise manner of how to plan the kind of creating a plan of how to go about that goal, and then actually performing that those plan of actions. That was the execution part, which involved motor skills. And then over the other end of the system, you start getting the feedback of the actions that the user has performed. So that is the evaluation part, in which the user views what is the change on the system screens and whether they are showing the expected outcome or not, whether they are giving some feedback that something has happened, something has changed because of my actions or not. All those mental as well as sensory interactions were there in the Norman's model of interaction. Okay. Now talking about the next part. So descriptive models are only for giving a description of the how the uh, interacts with the system, kind of how the user understands and uses the system. So that still provides us a lot of information about how the user will utilize our system and how should we make it user centric from the descriptive point of view. Now the other one is predictive and performance models. We studied a number of them now. So the types were, so computational models of the user behavior, and then formal models of interactive system. So when we introduced these predictive performance model, we incorporated the formal models as a part of the computational models itself. So formal models are also computational in nature. Hybrid models are not in the scope of our study, so we will exclude them. In the computational models, what we tried to study were these context specific behavior models, where the user is providing a input or making some motor actions or mental actions. So in the examples of these were Fitts law or Hick-Hyman's law, which we studied, or the steering law, all those things. And then we studied simple models of human information processing, such as KLM GOMS, that we have studied, where we talk about the keystroke layer movements of the person. So the keystroke level model. So in that we studied the different physical motor operators, mental operators, and how they how to calculate the entire task time. That was all that was done for the simple models of human information processing. We also tried to look at the how to interpret the one dimensional laws in terms of 2D and 3D mechanisms. So how to modify, how they are modified, and then how the constrained navigation happens. All those things we covered in the last few lectures. Now we are again, the cognitive architectures are not in our scope, so we will leave that part out, and we will move on to the formal models now. Remember that these formal models are also kind of computational in nature, so they are not like, they are not a part of computation, but they don't talk about the user's behavior now. So user behavior was considered mainly through these previous models. Now we will talk about the interactive system behavior. So how does the system imagine that we are now talking about the system layout mainly. Now, how should that behave? How should the interaction make changes to that? That is the most important thing now for us. Are left out. I think that hybrid are left out. I believe that because the scope has to be limited to the week long content that can be processed, so that is the only reason why they have been left out. Now, I myself have not studied those two, so I don't know why, whether they are more complex or less complex. So that way, I can't say that because they are complex, they are left out. That's not the case. I believe that one more reason is there, that for understanding the user centric perspective of these models, this much of information may be useful or maybe more valuable. That one that is covered within the scope of the project. That's why. Yeah, yeah. So I don't know how they sign the weeks. So yeah, but this question can be asked to course instructor Professor Samit Bhattacharya, because he will be able to answer this question. Why was this course constructed only for 8 weeks? Now, probably there are also requirement of the enrollment or something which decides the week long, how the length of the course. So maybe that because of that, this course is limited to 8 weeks now till now. So yeah, yeah. So I think maybe advanced course can be offered, but I believe that a lot of courses that, so this is coming from my own experience of NPTEL. Okay, this is not related to the NPTEL team members suggestions or anything. I am talking from my own perspective. It's my opinion that there are various courses which have advanced courses as well, but the research in those area, or the educational research in those area, have been going on since 1950s or 1980s. So these are pretty old subjects if you look at the timeline. However, user centric computing for human computer interaction is pretty recent as a course. So when we see the references of all the things that we study, they are so recent. They are from 2003, 1997. Some very basic ones might be from 70s, like 1968 or so, 1957 something. But the core crux of user centric models has come from the 2003, 2000, even 2010 and 2000 and 1997 area. So yeah, yeah, sure. Even though it is required for the developers for creating good softwares, I agree with you on that part. But because it is pretty recent, what getting grasping the basic might also be a very valuable thing. So that's why the course has been conducted for basic understanding, introduction to user centric. But eventually, I think in future we may have the advanced course as well. It will be really wonderful. We will now move on to the next part. So we will now talk about the formal models of interactive system. uh, yeah, so based on this modeling language that we use for the formal models, we have for the computational models, we have informal models which we studied, which we kind of discussed very initially. So basically all the descriptive models lie in this part, where we use natural language to model the user's behavior in terms of diagrams, tables and charts, or even natural language description also is a part of informal model. Then there were semi-formal models. So in semi-formal models, we still use specific notification instead of using natural language, like a simple English statement. We use a specific notation and there is a defined syntax. However, this defined syntax may not be really addressing all the semiotics. So a lot of natural language part also comes into this. Uh, the specific notation may not be really precise to a specific language. So now the talking about the examples in the semi-formal models, there is unified modeling language, UML, and then there are DFD, that is data flow diagrams. So those are the examples of semi-formal models. Even I think that ER model should ER entity relationship models would also, I think, fall in the semi-formal models, where they do follow a kind of specific notification of how the entity's relationship or the classes and the contents of the class would look like, should be represented, but they still rely heavily on non-formal syntax. So they have a defined syntax which is not so formal that it has to be kind of so two three people may have a little bit of difference between their syntax. The last one is formal models. So now today we are going to learn about formal models. They have follow a mathematical semantics. So the expression of this, what we say in this language, happens through mathematical means, and it has a precise syntax. An example of it is finite state machine diagrams. So still diagrammatic in nature. All three of them are diagrammatic in nature. You can see the difference in terms of the precision and the nature of syntax, semantics of the language use. So that is the based on the modeling language, we now will study some of the formal models which talk about the finite state machine. How do they incorporate the finite state machine? All those things. So important thing to note is that formal models are the models which use a set of measurable properties of the system, and so these properties are the states and actions performed in the system. So states basically refer to the layout components, what we see on the screen, and the actions basically are the interactions that we see that are can be performed on the screen. So to change the state of the layout. So that is the these are the set of measurable properties of the system. Now referring to those, depending on modeling language, we can have dash categories of models. See, that is correct. And thank you, Dr. Roy. I'm really happy to hear that you are using UX UI for the software development in your courses. This course is being helpful to you, and users are getting the results of what we are, learning. And it is always a good thing to apply what you are learning. The answer is three, depending upon modeling language. These three. One was the informal. One was the informal, semi-formal, and then formal. Yeah, UML class diagrams and DFD are the examples of. Again, another basic recall level question. The answer is semi-formal model. So these are not the confusion could have been between semi-formal and semi-informal, but the answer is semi-formal. To a formal modeler, design indicates a set of properties of the system that are measurable. Is it true or false? Sure, if we have some time left after the session, I can have a look at the screenshot of your software. Definitely, I would love to uh, get a, give a feedback on it. True. Okay. Now, let us take an example of the formal model. This example utilizes the power of. So we learned that it is basically a mathematical representation of or what we learn. So this is using a matrix and matrix algebra mode of mathematics to express how the push button switch operates a bulb. Okay, so there are two states of the bulb. One is the on state and the other one is off state. And the aim is such that whenever push button is pressed, either the on if the bulb is in on state, it will go to the off state, and if it is in on off state initially, it will go to the on state. So irrespective of whichever state the bulb was in, we the aim is to switch it. So that's why the model can be pursued in terms of this on state, that is 1 0, to off state, that is 0 1. So 1 0, we have to make this 1 0 to 0 1, and then if it was initially in 0 1, we have to make it into 1 0. So here the model can be constructed based on four parameters this in the matrix. Basically, why this ABCD four parameters came, that has been explained in the video, that because of the we are using the matrix multiplication as our means to express this formula or this model. We have one input side with the matrix dimensions 1 into 1 by 2, and the output is also 1 by 2. So that is the only reason why we picked four variables. So there is no other reason why this A B C D has come up. Okay, if we were expressing the same in terms of an algebraic expression, we may have used only two variables, 1 into a and z plus 0 into b, if that would have satisfied the criteria then. But using an algebraic equation would not give us this kind of state, so it won't give us a matrix. That's why we are using a matrix multiplication. That is why we require a 2 by 2 matrix, such that our output also goes in the 1 by 2 format. Okay, now this can be calculated based on this one. There will be one equation based on the when we solve the when we perform the actual multiplication in terms of a b and c d. There will be one equation in terms of a b c d. Rather than that, there will be one equation which will have a and d, the other one will probably have c and v, and then we can calculate the values based on this. And this has been done. The values are for a b c d, these are the values. So basically it's a kind of a diagonal opposite of the identity matrix here. So we can see that the values of a b c d are calculated based on whether the based on these two equations only, and then they have been populated. Now the limitation of this. Okay, so let's go through this first benefits of this. So there is first benefit, reachability. Okay, so the reachability means which of this state can be reached, state of the component can be reached. Remember, when we are giving this example, we don't have any screen option, right? We are not talking about screens here. But you can imagine that a push button can represent some keyboard key press or a mouse pointer click, all those things. So that's why it is a similar thing to what we are doing. And it's just an example which is much simpler than a complex screen. That's why this example has been chosen. The reachability is talking about from the on state where we can we reach the off state, and can we do the vice versa. So that that property is achievable in this model. Okay, so this state property of reachability is achievable. The other one is reversibility. So can we go from on to off, and then can we go back from off to on? So in the previous model we saw that we can model for both the states, so this model can be reversible as well. So this, for the push button example, when we have this model in terms of ABCD matrix and find out the values of ABCD, both these things can be done. Now the third thing is the dangerous or unsafe state. From this model we may not be able to find the dangerous or unsafe state, because there this push button operation may be very simplistic, so we may not have an unsafe state. Unsafe state actually means that we may not be able to define what the state is. So there are some cases in which race conditions happen that we may have studied in, if you have studied the logic gates and all, may be aware of a state which is called as a race condition, which is not good practically in a component, in a device. So such unsafe state where the predictable exact state of the thing may not be predictable, so that is the unsafe state or dangerous state. That here in this example it is not predictable. Similarly, we can identify one constraint of this, but there is one this benefit. This is a benefit of this modeling, even through push button, that in a bulb replacement situation, say our bulb fails. So now we cannot determine whether while we unscrew the bulb and want to change the new bulb, is it safe or not to unscrew the bulb in the first place. So if the state of the switch was on and the bulb was off, the bulb was defective, so that's why it is off. In that case, if we try to replace it, there might be shock. So that's why it is not useful. This push button is not useful to use. This push button model is not useful to identify whether the bulb is on or off while it was damaged or while the defect occurred. So that is kind of a constraint that we identify when we model such systems. So that is another benefit of this exercise of modeling a system, where we can find out whether the system is reachable, where the system states are reachable, where they are reversible, and we can identify what is the constraint of that model, so that we maybe try to create a better way of layout or better way of representing the model itself. So an example of this problem solution, here instead of a push button, if there were a kind of start and stop, two push buttons were there, one would always be allocated to switching on operation, one will always be allocated to switching off application. Then even though the bulb was defective or not, we can identify whether there is a defect or not. So whether the switch is on or off. Even if we don't identify, when we click on the off button switch, we can be ensured that the connection is off. Now it is safe to remove the bulb. So that is the benefit of, if in case we wouldn't have modeled this initial push button switch example, we would never have found out that this problem would not be solved. So that's why modeling is beneficial. That's what we are trying to say through this example. So we looked at the state properties that this formal model gives us. So one of them is reachability, reversibility. The other one was this unsafe state, which is another state property, but in this model scope we did not look at any unsafe state, but we looked at this constraint. Then we look at the action properties that are associated with this formal model. So one is the completeness action property. Okay, so in terms of completeness, what we want is that the model gives an exhaustive view of all the actions that can be performed, all the interactions that can be performed. So, this property of completeness is talking about all the exhaustive options, that interactions that can happen within the model, and all the exhaustive changes of the state. So that is considering the completeness property. That is the complete benefit of completeness that we get while making a formal model. The other one is determinism. So determinism is basically the finding out which state. So there are some models in which you perform the same operation but you reach a different state. For example, if I use a escape key here in this presentation, I will be going out of the slideshow mode, right? So that is the purpose of escape key for me over here. But while using some other application, I will still use the same escape key, and that's use might be defined different. So the state over there will be defined differently, and the state over here will be defined differently. Even though the same operation is happening, its effect or the state changes with respect to that operation will be different. Even though it is different, it will be deterministic. So it will be we will be able to determine what is the state change based on the model. That is why it is a property of the actions of the in the formal model. So it is an action property. Determinism basically means performing the same operation yielding a different result, but still that different result is deterministic. So it is not randomly happening. So when I press escape, something random doesn't happen. Something that is determined for that particular application or the layout, that is only the thing that is going to happen. That is why it is deterministic. Now, how are these properties ensured? We have three techniques. One is model checking technique, theorem proving techniques, and then there is equivalence checking techniques. All three are not covered in the coursework, so we will not be going over them. So I wanted to have this question asked. Some of these techniques may be covered in the book or somewhere else. If you want us to go over them, I mean, there is an option of having an extra lecture. We may have 1 hour extra lecture, extra session, but I was hoping that we can stick to what is asked throughout the course itself. So that's why I was not trying to opting for the extra session. But if there is you can give a feedback in the problem solving session or on the videos, so that I will think about whether we should have an extra lecture. So in that extra lecture, maybe we can go over some of the content that was not covered. Maybe not in detail. Probably we can go over why this model checking technique, why to go for theorem, or when to go for theorem proving techniques. That way we can maybe do. So I won't be able to go through. If these are really complex mathematical things, we may not be able to cover it within 1 hour. So that's why, yeah, so some pointers related to those maybe we can cover. Now the next is question. Determinism is so for the purpose of this course and the course examination, you can expect this. A state property. Oh no, determinism was a action property. So the state properties were reachability, reversibility, and dangerous, identifying that unsafe state thing. And completeness and determinism are action properties. Okay, yeah. So the answer is B, action property. Components of user computer dialogue. So we have modeled all these things. Previous models were basically talking about the user's behavior. Now today's session we are talking more focusing on the user computer, so the computer's interactions rather than the more towards the user interaction. So we are modeling the user computer dialogue essentially in today's session. And the two parts of this dialogue are the interface itself, the view, the layout, and the second part is interactions that we have performed on the system. So interface basically represents the state, can be represented using the system state, and interaction are the state transitions that occur. So if you read some of the examples covered in this week, the state transitions basically are not just mathematical expressions. They are also, some of these are uh, actual English verbs that we have used in the example models in this lecture. So one of the examples of this is hierarchical state transition networks. I'll just have some water in a minute. Okay. Hierarchical state transition network. So previously you must you since you are from computing discipline, state transition model networks, state machine diagrams, you may be aware of them already. So state, I will just, for those who are not from computing discipline, if they are watching our video, I'll just give a little bit of example. So basically you have models like this. You have some state S1 and there will be some state S2, say S2. State means how does the a particular object look like. At a in a very layman term, it is how does an object look like. And there is a way of going from this state 1 to state 2, and that way would be like this, from state 1 to state 2. Usually it is represented by a curve, and we will call this with a transition. So T1, T1. Yeah. And similar way from state 2 as well, we might be able to go back. So that will be S1 to S2 to S1, and that might be, we can call it as T2. So this is how we represent a state diagram. Sometimes the state itself has some transition, an action or an interaction which leads to the same state. So then the arrow is kind of shaped like this, S1 going from S1 to S1 itself. So that is how we have state diagrams created. T1 and T2 are the transitions, that is the interaction, and S1 S2 are the states, which is the interface state. Okay, now we will go to the next part. So hierarchical transition networks, in this we consider that an entire system, when we talk about a whole system, we have so many components of a system, on an application or a system or a software, whichever you call. So we consider in the hierarchical state transition networks, we consider it entire system as a hierarchy of subsystems. In the subsystems there are a lot of sub dialogue models that happen. Okay, so when we try to model a system, we are trying to model the hierarchy of these sub dialogue models. Sub dialogue is the interaction between these subsystems. Okay, so we try to model these sub dialogue models with a higher level connections in between these subsystems. So there are connections, there is a dialogue as in what would the users input of what will the users put as an input, how will they affect the state, and even the interaction within the system, how will that affect the state. All that is the dialogue. So we are trying to model the hierarchy of these subsystem and sub dialogue models, or sub dialogues that happen. So the aim while we do this hierarchical state transition networks is that we divide the big model into subsystem levels, such that there are less number of variables in the defined states as each subsystem level, so that we can make the modeling manageable. So we see in the video lectures there is an example of alphabet representation on screen that is given, and we will go over that example soon. In the next few slides we are going to go over that example. Basically, even if you imagine just a simple thing, just a simple character A on your screen, displayed on your screen, still if you try to model the A and changing the font or changing the letter or changing the size of that A, font size of that A, only that much change or that much interaction is also having a big chunk of model steps. So there are different, sorry, not model steps, a big chunk, a big number of states that can happen. So possibilities of changes to A that can be done. So that model becomes so complex that there will be so many number of individual states, and there will be so many connections within those states. So it doesn't look really, understandable to the designer. It is not useful to have a go on adding information which cannot be processed. So to make it easier and manageable to model, what is done is you represent the system in terms of subsystems which are layered. So you consider a hierarchy. First, what will happen? Second, what will happen? Third, what will happen? In each level, second level, third level, what are the different subsystems that play a role? All those things we try to model using hierarchical state transition networks. One challenge of this, there are two challenges of actually of this hierarchical state transition network. One of the challenge is that which state of sub dialog should be entered first, that is not known. So when you define each individual step, uh, each step doesn't actually speak about when that step is entered, or when that subsystem is entered, what is the first value of the state, or what is the first state of the variables that lie within it. So that is not shown in the hierarchical state transition network. And then there is also lack of support for having concurrent behaviors. So if there are two three systems subsystems which are behaving even at the same level, it does not mean that they will all function concurrently. So there is no option to have representation for two different types of changes to that alphabet example. Okay, so there is no option to have two different type of changes happening simultaneously. So that is the problem with hierarchical state transition networks. We will have an example of this hierarchical state transition network as well as the next part in the session afterwards. Okay, so the answer to solving these two issues, one issue was that there is no there is no way to know which state will be entered first of the within the subsystem, and the second one was there is no option to show a concurrent behavior. And to address these two, there is a option of state chart. So basically, most of the lecture, I think 24 or 24, focuses on explaining the state charts. State charts will be the formal modeling language, the language or tool that we will use, and we will study its basics. What state chart does is it incorporates state transition networks. It incorporates the hierarchy. So initially the hierarchical state transition networks only had this much part. Now state charts also add concurrency and communication to it. We will look at how it adds the hierarchy and concurrency to the initial hierarchical state chart. So the state charts are advantageous to the hierarchical state transition networks in the way that it talks about both the initial historical state of the each individual subsystem. Also it talks about the concurrent operation between the two subsystems, between any two subsystems. So that's how state charts are different. So some let's look at what are the basics of the state chart. So it contains many useful elements. Some of these are super states, basic states, default state mechanism, history mechanism, and then there are and super states. So what are these? We will study in the next few slides, starting with super states. So there are two types of states. One is a super state, one is the basic state. A super state is basically encompassing the basic state. So it contains some basic states. This basic state that we represented using this circular diagram, circular notation, and super state is represented using a rectangular notation, rectangular box around that super state, around that basic state. So basic state may have only single state, or it may have two different states. Sorry, basic state will be represented by a single state or two different states, and super state will encompass those two states. For each basic state there is a super state, which is also called as an ancestor set of the basic state. So ancestor state is another name to this super state. So here is the example. Super state is labeled like this. It is represented by a rectangular curved edges rectangular box, and basic states are B1, B2. They are represented by an oval or circular example. Yeah, this is the example. We have this representation, and within the basic state there would be transition T1 to go from B1 to B2. There would be a transition, that is an interaction T2, which causes B2 to go to B1. So these are basic states. Super states is nothing but the ancestor state, or the for these basic states B1, B2. So each super state may contain single basic state or multiple basic states. If a super state contains only single basic state, it is called as the OR super state. Okay, so this is the single state machine. So that is this is the OR super state. Now in the state we have what well, let's go back now. Yeah, so there is super state. We covered what is super state, we covered what is a basic state. Now the option is to cover what is the default practical example. Okay, example of an interpretation. Okay, so talking about this on off state, so B1 represents 1 0, B2 represents 0 1, T1 represents what is the transition that we do on off operation to go from on state to off state, whereas this T2 represents a transition off to go from this off state to on state. Switching on, switching off will be the transitions. On and off, 1 0 0 1 will be the state, basic state. And containing this entire thing will be the subsystem. There will be the super state, which is maybe the switch state. Okay, so that way we can interpret it. Application, how and where. So I think every example that we have studied so far, every example, if you want to model it in a formal language, this is the mechanism that we'll use. The reason why we did not use previously was that we were studying the informal and semi-formal model notations. Now that we are going into some of these examples, we will have a few examples in future also. We will make this super state, substate, all those things for this alphabet example in the later part of the session. So there I think it will be more clearer. Now another thing is this default state mechanism. So in every state box, in every super state rectangle, we have one this notation with a circle, kind of a bullseye kind of mark, and this arrow pointing towards which was the first state, default state of entry. So this is how the default state of entry is represented. But now, say in the beginning we have the default, all enter this super state, and we have the default value of the b2. So we want to start with b2, that is known. But now, say we have performed some operation t2, or then t1, then again we have performed t2. Now the state is t1, b1. Okay, now again we exit this state and perform some other operation. Then when we come back, we want to now locate to the b1 state, not to the b2 state. To give you an example, again we will talk about that bulb example. Initially the bulb was supposed to be off, so the b2 represents the off state. We enter the off state, so the default state is remembered. We enter the off state, we perform some operation, we try to click the switch on, and then it enters the on state, b1 state. Now we have left the system, so we go around, we leave this switching on and off, we do some other activity, and then we come back to this state. Now the bulb is showing on side, showing on to us, but there the state machine would again go back to the default, right? So to prevent that from happening, to prevent us from entering the off state, what is done is, there is also a history state. So this history state is basically a kind of memory mechanism, in which the exit instance state of the variables, or the state is recollected. So when we exit this system, we make something t3 with other state. What we do is, we still in the h block we will remember that whether the bulb was on or off. So that is the biggest advantage of the state chart, where we have a history mechanism. This history is always recollecting the current state of the changing variable. Now here they are showing the example of how the representation is done outside of the super state. So if I want to have this b1 and b2 operation, so essentially think of it like there is a component on the screen. Okay, if I think about it like a component of on a screen, a push button, or a so a push button, or a bulb like example. uh, it is basically these two states within this super state are about the same component, right? The component of bulb, switch is the same. So this entire super state is representing the switch, but the switch has two states, different states. That's why there are two basic states within it. Now if I want to utilize this switch again outside of this super state, I want to make some transition to this. So in case of a switch, it is difficult to give an example of this outside transition, but maybe considering a push button or a layout component, I'm considering that I want to make some operation about it, which will lead to the another state of the same thing. So then in that case, the representation is not like this. So within the super state, we don't go drawing the arrows, we draw the arrows outside of it. Okay, so the b3 is again another state of this b1 variable. Okay, so if I talk about the states in terms of variable, then so maybe when we go to that example of a b c, typing a, we will again revisit this. What is this? We went through this history mechanism. Then the last issue was the concurrency. So for concurrency, we have this super state which contains two different subsystems. So there is one state machine about b1 b2, another state machine diagram of b3 b4 transitioning to b4. So there are two different components of the system two different part of this model, b1 and b3, b2, b4, which happen concurrently. So this representation of this dotted line is the thing that separates them. So we know that these are not connected to each other, these are not part of the same variable that we are trying to change, but these are the two different variables which will change concurrently at the same time. So this is the and relationship. So and relationship as in, at the same moment, if I want to change the font size of a variable as well as change the color of this a variable, all both those things will happen concurrently. So this is the old assignment question. Basically about a notation, recall level again. We will go through an application example, okay? Yes, the letter H. No, so the answer is not letter H within a rectangle. Superstate is represented by a rectangle, but the letter H is represented within a this circle. So historical state of this variable that we are talking about in B1, that state that is saved in the H within a circle. So B would be the correct answer. Next, in state chart for basic state, there is a super state which is also called the dash state. No, it is B. Correct. Next, this one. And again, another recall level question. Mostly, I thought that within this times assignment, there are more recall recollection type of questions. So here each superstate of the basic state is called as ancestor. So A is the right answer. Let's go ahead. State notation supports state chart notation supports concurrency. True or false? True. Right. So hierarchical state transition networks did not support concurrency. State chart notation does. When a superstate is entered for the first time, the dash mechanism is followed. For the first time, so here maybe I did not cover that, but when the superstate is entered for the first time, we go to the default state, and when it is entered later on, we go for history mechanism. So apart from the first time, it goes for the history mechanism. For the first time, it will go to the default state. Okay, so some of the times even the default state is also marked at the H box also. Okay, so that is also kind of convention. So probably here we saw that example, right? Yeah. So here you can see that the default state itself points at the history mechanism. So even that kind of notification gets followed. Now we will look at the single character on screen example. Imagine that there is a system where we can see a single character on the screen. Let's take for example A. We can change this character font size. We can change this character A to any alphabet on this on our keyboard, and so there are 26 options. We can change this character with left or right arrow keys. We don't have to enter the keyboard keys. Okay, that is the way we are going to shift it. Next, we can imagine that font size of this A can be changed up to 8 options. So that can be done. If we want to increase the font size, we press the up arrow. If we want to decrease the font size, we press the down arrow. Then we can imagine that font color can be changed. So for changing the font color, we can use the space key maybe, or any other key for that matter. Only there are two color options that we are considering. That's why we are taking only single key. Now remember why we are doing this. We are not talking about our keyboard in general. We are talking about some design which will make all these operations, which should be very small size design that can perform all these things. So that's why we chose very little number of keys, left right arrow keys, then up down key, and then one single key to perform all these operations. Even though there are so little number of keys present in front of us that we need to operate, there are, if we model all of them, there are 26 into 8 into 2, so there are 416 options of changes that can be done to this state of the interface that was only showing A. Okay, so these are 416 options that, or different states that A can go to, because there are 26 into 8 into 2. Now that is why we require, modeling all those 416 would be so cluttering. So that's why we are trying to do these two types. One was the hierarchical transition model, and then the other one is the state chart model. uh, Hierarchical one doesn't have the super state basic state representation, but we will go through the super state representation only. Okay. uh, Basically, this super state is kind of providing us with a very sophisticated view, a very manageable view. If suppose we do remove these super states and just try to map each and every state to one another, that is how the hierarchical one would look like. That is a big problematic thing. So that's why we went through state chart model notation. In this, these three parts of what we want to change about a character, that those are shown. So we have seen this character is a super state. In the character state, we see the two values of this variable character. So this was initially, that was a. If we press the left arrow key, so left arrow key basically is for going one alphabet before that, the existing one, the current one. So if we press the left arrow key, we will still stay on a. Then if we press the right arrow key, we will go to b. When we are pressing the right arrow key going to b, and then we want to come back to a, we can have left arrow, press the left arrow, so we can come back to a. The character would change to a. Now instead of modeling all the ones, so actually we are supposed to model from b to c to d, c to d to e, all those things in step. Just like this, there will be so many circular transition diagrams, but then it would be cumbersome. That's why this shortcut has been followed, but actually this shortcut does not exist in the state chart method. Okay, so that's why for something even having 26 only states, we still have cumbersome effort to take for modeling that. Last part we can think about this. So when we reach z, even though we press the right arrow, there is nothing next to z. Either this z can be connected to a if we want to again go back to changing towards a, or it can be like when we press right arrow, it stays as z. Okay, so these are the two ways in which left arrow right arrow functionality can be explained. uh, in the here also you can see the h block in the within the circle. It is not the letter h, it is the historical state. So by default we go for a, and if in case we have modified this a, press some left arrow 2 3 number of times, then the changed letter would be stored in the edge state, and and we will point towards that letter in that state part of the state when we enter this character block again. So now, putting it in an example of our regular screen, maybe I have a instead of this character screen, I may have the some other element, this menu as a super state, and within that menu I have file, and then I press the bottom arrow to go to the next menu, like new menu, so the new option within the file menu. So this is how we can model the system in a formal language, in a formal notation. So this was representing the character superstate. Similarly, there is font size superstate and then color superstate. Each one is having a transition that is represented by key press in this case. So you may have a transition represented by click of an mouse click as well. So depending upon what is the operation that you are performing, what is the interaction that you are performing on the interface layout component, this is representing the value of that interface layout component. This is representing the component's name, this is the value, and then this is the interaction that is being performed. So that is how we will model the system within those systems. Now I want to stop modifying the color, and I want to start modifying the font size. If I still press the space key, it won't go to the other superstate. That's why a different key press action needs to be there. So that's why this up down key was chosen. So instead of up down key here, it may have also been left arrow, right arrow, that would have also worked here. Okay, because left arrow, right arrow is not utilized within this state. Next we have clicked on up down arrow, and we went to the font size menu. Now here again we are using up down arrows. So that's why to exit this state, they have not used the up down arrow there, they have used the left right key. Yeah, so that is why these within the states, different super states, the interactions are represented with different interactions are different represented with different operations, which are exclusive of what is the operation happening within the state. This is, I will tell you, this is again a very simplistic example of just having one character on the screen. If you want to model so many things on the present on the screen, this is going to be a big model. So there is a big I mean, this transition need to be very specifically chosen. So maybe we are thinking about the screen that is present in front of us, and in that case it becomes a little bit simpler, because instead of left arrow, right arrow, we are not just using this arrow keys, right? We are not limited to the arrow keys. We may say that pointer moves to this, pointer moves and clicks on this particular element. So in that case, instead of using the keyboard for navigation, we may be using pointer device, so that we save time. Ultimately what we want to do is we want to save the user's time. So these here the we also want to we have like 2 3 things in mind when we are as a software developer creating this software for the user, right? One is as a software developer, reduce the cost of creation. So that's why when I have this aim of just having displaying a single character, I considering the cost from the point of view of software designer or software developer, what I try to do is, instead of designing a big keyboard, I will design only a few keys that can be useful to manipulate this character on the screen. However, when I go towards making it user centric, I have to think about all the operations that can be required to modify this single character, and in that case I may end up changing the decision of uh, cost cutting to prefer the user time that needs to be spent. So that is a critical trade-off that user centric developer would have to address, whether you want to address the need of the user, how much satisfaction of the user would increase by just incorporating some costing element in the system, right? For example, if you can see this character block and you saw that there are so many states that it is doing. If this cost of making the user change perform actions, this right arrow press action or to change a single character uh, is costing me, if the user gets tired, like for example a user can see a character A on the screen, they want to change it to H, they have to click on the right arrow key for so many times, 8 times to reach H, or 7 times to reach H. So say because I'm making the user perform this action so many times, I'm wasting their time, I'm making it cumbersome for them. So if that is going to cause the user to not come back to my application, to not like my application, then it is better to invest, have some software, to invest some cost in the in terms of creating this keyboard in front of the user, instead of having multiple 626 keys in front of the user to pick a any character easily, than making them go through the right arrow press operation. So that is how this model would benefit us to make a cost wise decision as well, like whether the trade off between this time and cost uh, can be is important for me, how to interpret this or how to make a decision based on this trade off of this trade off of time, users time and user satisfaction, and this cost of my software. So this is how these type of modeling can be useful. So if I had not chosen to model create displaying a single character A would be a simplistic job for me, but because I have tried to model, I understand the niche of this, or the technicality within the system which needs to be addressed, which may cause the user a lot of time, a lot of pain to use my application. So that is the benefit of this modeling practice. So this was one example in which you see each of these as a singular super state which can be modeled. Now we will see what happens when we try to do the concurrent system, concurrent states. So in this super state, we are combining the previous two, font size and character. So the sub dialog for font size change still remains the same. It still is this cumbersome diagram, and within the sub dialog for character we still have this cumbersome diagram. It needs to be represented in the same way that has been represented over here. Whereas there is another super state like color. Why this is example is given in this example, when we would not have two different actions, like previously there was up arrow, down arrow, then there was right arrow, left arrow, no, so the actions to modify was the different, but now we will not have a modifiable different modification for two of them. We will have the same mechanism, up arrow or down arrow, or up arrow and down arrow, or right arrow and left arrow, either of them, to change these characters and the font size. Both changes will happen concurrently at the same time, and that's why, because we cannot use the up arrow, down arrow, we are using the space key. Within this colors subsystem, if you remember, we were using space bar to change the color. That's why to go from color to the font size character, we don't have the right arrow, left arrow key, we have the space bar key. Yeah, I think the arrows pointing are different way. So here left, here it should have been space bar. Sorry, I navigated through different. So no, actually, it should be the space key to go from this bar pointer to the color pointer, since within the color pointer we are using the space key, right? So to exit this color state, we need the left right arrow key over here, and the space key should have been here in this example. So that's the example of single character on screen. Now we are going to the how to study the VKB case study video. So there is a case study video that is provided lecture. Um, we are sort of at the end of today's session. How to study the VKB case study video. Okay, so the reason I incorporated this case study, so now the assignment questions of the old year are over. This is an extra thing that I will cover in today's session. uh, that is going to help you with there are two case studies. I think previously also we had a case study in one of the one of the lecture series, one of the weeks. So how to approach these case study videos, we may just go on watching the video and then towards the end of it understand something, or maybe we would not understand at all. So my method of understanding a case study video I'm just sharing with you. So what I do is I try to recall what we have learned in the previous thing. So we saw that there are three layers. We are talking mostly about the application software layer in our study. There are three sub layers within this application software layer. If we talk about the user centric computing, if there it was not user centric computing, this second sub layer of user state predictor is not in the picture. Now think about these three blocks: input provider, collector, renderer. This user, whatever the user enters, that is entering as an input provider to the system. Collector is something that values that the user state machine predictor stores within the collector as a current state. So here I think when we have modeled those formal models now, we will have some idea about the historical states and the default state. All those things, states will be collected over here for each and every super state of the of the entire model. So that collector's job is the kind of storage keeper. Similarly, collector's job is also to if a user state predictor has calculated some value of a speed or through the model, or some value of a, so the outcome of that model, that also gets stored within the collector. Okay, so collector is important if you have to model use an specifically mainly when we are doing the non-adaptive models. We don't even have the input provider, right? So at that time, collector is the one that gives us the user centricity, maximum user centricity, because that provides the current state and the calculated model values which are empirical in nature to the user state predictor. Then the user state predictor is going to pass on the decision making interface state predictor for pass on the values for that come out of our model to the interface state predictor. So if you were modeling attention, they will pass on the attention model value. If you were modeling the difficulty, then they will pass on the index of difficulty value. If you were modeling for task execution time, user state predictor will give the task execution time to the interface state predictor. What the interface state predictor would do is it will consider will it be H, which one is collector behave as it. So collector does not have H is within the a super state. There will be the initial state of the each variable, we can say, each state. that has been changed. The collector contains all the superstates. So within that, each superstate there will be some H historical state saved. So collector, you can imagine it as basically a repository of all the superstates, with each superstate having its individual H. So there are multiple H storage values stored within the collector. Yes. Then interface state predictor will provide the input to the renderer to what to show on the screen. Now that's why what would each block in the application layer of the virtual keyboard will do. So while the case study focuses on virtual keyboard, you should think about how the virtual keyboard how to fit all these blocks in a example of virtual keyboard. So the input provider, whether it is needed or not. So if we want to model the virtual keyboard, we may want to go for the non-adaptive keyboard layout style, so then we don't need the input provider at all. Then we think about if we want to make that also adaptive based on each individual user's input, then we will need the input provider. And that in that case, what will the input provider provide? The user specific action time, or the user specific keyword words utilized by the user. All those things, the user's input uh, is provided, and they are also getting calculated. Now the collector, what information would it collect in that case? For a virtual keyboard, the key pressing time, the task execution, the initial keys pressed, or the time taken by the user to press those keys, or the empirical values of all the motor actions that we initially calculated. We have seen those timings for expert, novice, and intermediate users. What were the timings? So all those values, initial values, will also be collected by the collector. Next, what would the user state predictor calculate? So the predictor may calculate the task execution time for this particular user in a particular layout. And what decision would the interface state predictor then make? Based on this task execution time, there will be different types of layouts, right? So we will consider different models, and we will try out these different models within with this user. And the interface state predictor might then choose which one of these is suitable for our trade-off for time and accuracy. And then this interface state predictor will share that specific layout for the renderer, and then renderer will take care of doing for displaying it. So think, when you study the case study, think about these individual components, how they are doing, what is the job they are supposed to perform, and then studying it would be easier. So next, in terms of the model that they have given, that for the virtual keyboard design, there is a metropolis algorithm which can be used. Zai et al. Has introduced it in 2002. Basically, there's a question in assignment this year based on this algorithm. That's why I chose these two slides. Just an introduction to this algorithm. So the technique, very minute details I'm not covering of this metropolis algorithm. Basically, metropolis algorithm, what it does is it represents this subsystem and system in terms of it kind of has an analogy with the energy state. So just like energy state, we think about in terms of this molecules and of chemistry, we think about the system as if it is a molecule. A keyboard system is a molecule, and we think about this this molecular system has an energy value. We assume that the average movement time for keyboard layout movement or keyboard pressing, that is the energy state. The aim is to have objective is have the layout that minimizes the average movement time for the user, so the user can have less movement time, and then they can type in faster. So the task execution time for the user will be should be low. So that is the minimizing is the main objective, and for minimizing that, the average movement time is inversely related to the typing speed. So we want to increase the user's typing speed. So that is the main objective of this Metropolis algorithm, to increase the typing speed by reducing the average movement time. So that's where we are at the end of week 6. And I think that this question about in the assignment can be answered with this much use or this much information. uh, Basically, there won't be questions about the details of this variables that are used in this variable in the algorithms. Or usually, even I have seen that there are very less number of graphical questions asked in the examination. So from the exam point of view, we have covered maximum part. Now if there were any questions, you can